Good morning.
Morning.
Good morning. So we are discussing here if you want to choose easy option for today or difficult option for today. Difficult?
Yeah.
You have two easy ones. Then we can pick something in between. So easy option is just summarize what we learned so far. So you know the material already, you can look at the bigger picture and see what we learned so far and how we can use it for something useful. The difficult option is to continue this Lyapunov stability. And this includes all kinds of positive definite matrices, it includes norms, it includes limits, calculus, and sophisticated functions which nobody knows how to develop really. It's that kind of difficult.
Then I think I know that
Yeah.
because there is summary of our.
Well, we will need to do some midterm summary of everything just to give a bigger picture because I will be building based on that picture, I will be building future lectures. But this kind of lecture is not directly related to the big picture because in that lecture, we will talk about stability, we will talk about different kinds of stability and how you define stability in general because well, stability is not really very well defined. We know about asymptotic stability, we know about Peeble stability, but you have other types of stability, actually many other types of stability because what you define as stable, it depends on the system and depends on what you want from the system, how you want the system to behave. Right, so based on that, you will know what you define stable or not stable. And we will talk about a few different types of stability. This will let you just know a few other types of stability, which are useful for different kind of systems. And we will define Lyapunov stability in that lecture.
I have a question.
Yes.
In our post, I'm saying that in November 18 or December 2, there is something 5 to 8 p.m. What is that?
I'm sorry?
November 18, 5
November
to 8 p.m. There is
18th.
I mean, in my calendar showing that model control theory.
What does it say? Some kind of assignment? And something. This looks like a Zoom meeting. It's something. It's probably was copied from the previous year by mistake.
Okay, yeah.
I will remove it.
Okay.
Okay. All right, before we start, any questions on the homework? Any questions on the previous lectures? Anything that you want to discuss? Okay, so today we are getting to the peak difficulty of this course. Okay. We will go slowly. This entire lecture is probably like 7 slides or so for entire hour of work. So we will go slowly and I will try to explain different aspects that you might not remember from linear algebra, from calculus, from other places, which are very useful for that particular lecture. Okay. And if you have any questions, you just stop me in the middle. It's very important that you will get the essence of what I'm talking about and maybe not all of the details of the formulas of how you develop these formulas, but the meaning, what it means, because this is the important part in that lecture. So today we'll talk about Lyapunov stability and how Lyapunov defines that was 100 years ago. And practically speaking, this was one of the first definitions of stability. based on the energy functions, and it came from physics for obvious reasons. But the definition was purely mathematical and a little bit complicated, but that's okay. The reason to define that new type of stability, which is not asymptotic and not BIBO, different kind of stability, is that asymptotic stability is too strong typically. So it requires that the system will not only be converging, but also will be converging to a particular point all the time from any regions that you want, and so on and so on. So it's kind of stronger type of stability where system is not only not diverging, but it must converge, which is not the same thing, right? So Lyapunov stability will tell you, well, a little bit weaker type of stability where the system doesn't need to diverge, but it doesn't have to converge as well, okay? So it's not moving too far away from its initial position. This is overall idea of the type of stability. And also another thing that nonlinear systems, for them, it's very difficult to use linear methods to define their stability in general. And I'm talking about stability of any equilibrium points anywhere in space. Okay, so sometimes you can do that, sometimes you can't do that. Sometimes you have zero eigenvalues, you cannot do anything with that linearization. Sometimes you cannot even linearize a system. So like, what should you do in that case? So for that, you have other types of stability, and they work both for linear systems and nonlinear systems. So you can identify stability of nonlinear systems using Lyapunov stability methods. All right. Here we go. Okay. So first of all, we define the stability, and we call it internal stability in continuous time, or Lyapunov stability. Internally stable is equivalent to Lyapunov stable. And here's how it goes. Let's say you have some nonlinear system defined in state space representation, and this system will be x dot equals some function, potentially nonlinear function of x and t. Obviously, this is a vector of functions, this is vector of states and time, right? Now, pay attention that I don't care about the u part here, because we are talking about stability from particular initial state, similar to asymptotic stability. If you remember, asymptotic stability means that from any initial state, you converge into zero in linear systems. This asymptotically stable system. So converging to zero from any state. So it's not diverging and not staying wherever it is, it's just converging to the 0 point. All right, this is asymptotic stability. BIBO stability was for input-output, bounded input, bounded output stability. So this was for zero state, and asymptotic stability if for given state, initial state, and zero input. So it's zero input response. Same thing with Lyapunov. It's zero input response. This is why I'm not using any u here in that equation. U is zero in that case, so I don't care about B vector. And also for linear systems, at least, that A part is defining your stability. Eigenvalues of A define your stability, right? So you don't care about B vector, what multiplies your U, right? So your stability is not dependent on what multiplies U or how U enters the equation. You care only about the X part and how X is changing inside somehow. So that's why I'm defining that function like that. You have also initial state, which I call X0. Okay, so far, this is state space representation. And we are talking about equilibrium point. How do you find the equilibrium point? The same way we found it last time in previous lecture. We're just taking x dot or f equals to 0, solving that system of equations, finding all of the x equilibrium vector, right? So this equilibrium point is internally stable or Lyapunov stable if for every r larger than 0 exists some other smaller r as a function of r larger than 0, such that norm of x0 minus x equilibrium less than r. If this is true, then this is true, which needs a lot of interpretation here, right? But if you know infinitesimal calculus, then you kind of seen that thing before, in a way, if you learned calculus in math department, not for engineers, because mathematicians using that type of notation all the time. They define integrals derivatives using epsilon delta notation. That's how it's called. It has even name. Epsilon delta notation is how you define limits. So if your particular variable is close enough to a particular point, and it gets as close as you want it to that point, then some other difference is less some predefined constant, which will be a function of the distance from that point. Okay, this is how you define it. So let's try to give all these variables names and try to understand that graphically, how this criterion is defined really. So here is what it says. Let's start with two-dimensional space, where it's much easier to visualize state vector. So let's say this is x1 axis, and this is x2 axis. So you have second order system with two axes, right? Your state is two-dimensional, x1 and x2. So what does it mean x1 as a function of t and x2 as a function of t when t is changing in time from 0 to whatever time? This means that you have, for each given time, you have point in that two-dimensional space. So it's somewhere here, for example. This is your initial point, x0, which would be x1, 0 and x2, 0, right? That dot here, right? This will be your x0. So starting with some initial conditions in the two-dimensional space. Now, when time passes by, your system is working, doing something, your states are changing in time, right? So each one of them is a function of time. x1 is a function of time and x2 is a function of time. But if you're drawing these functions of time in the two-dimensional space, what do you get? You get particular trajectory, which means line which is kind of moving around somehow. Based on the system, you'll have different lines. So this is a black line that you have here. It's kind of moving, doing all kind of things, wiggling. It could be converging to 0. It could be diverging. It could be all kind of, depends on the system, right? So it will be some trajectory in time. And for asymptotically stable systems, this will converge to 0, 0 eventually, if you don't have any input, right? So you have some initial conditions, the system is stable, you have some of the exponents, all of them are converging to 0, right? The solution of linear equations, differential equations. So some of that will eventually converge to 0. So this trajectory will do something and then get back to the origin eventually with time. Okay, so practically the points on that line are functions of time. Okay, for different times, it will be at different places on the trajectory. Clear so far? This is base space. And it is used a lot in nonlinear systems, that type of representation in coordinates of axes in state space, right? So here's a claim. The system is Lyapunov stable if you pick particular radius r, which is capital R, okay, you give me the radius, circle around that point, origin point, okay? So you can pick it as big as you want, you can pick it as small as you want, okay? That's what I'm saying. You can pick it super tiny if you want to, like really, really, really close to origin, or you can pick it like 1 million, whatever you want, okay? So pick your radius. So my claim is that if the system is internally stable, I will be able to take your radius and to pick smaller radius, which I will call not capital R, regular R, right? That R. So obviously it will be a function of your radius. If you pick that kind of radius, I can pick that kind of radius. If you pick that kind of radius, I will pick even smaller radius, okay? So I'll always be able to pick a little bit smaller radius such that if I'm starting within my smaller radius, which means my initial conditions are starting somewhere inside of that smaller circle, okay? So I'm starting somewhere here or there or anywhere inside of that circle. Pick any point. So if I start within that circle, that's what that thing is, okay? Then my state for any t, like for t from 0 to infinity, okay, for all times, will not leave your circle. It could touch, maybe, so it will be equal here to R, but the trajectory will be always inside that circle, bigger circle that you have picked. And this will be true for any circles that you pick. Okay, you can pick big circle, you can pick small circle. I will always find even smaller circle that if you start your initial condition anywhere within my smaller circle, it will stay within your larger circle. Your trajectory will always be within the bigger circle. This is what it means, internal stability. And obviously that type of stability is very difficult to apply in practice, right? Like, how do you know you have infinite number of possibilities for initial point within my smaller circle, right? Also, you have infinite number of possibilities for systems, for trajectories inside, and it's also n-dimensional, not two-dimensional in general, right? But the idea is the same, and this is, first of all, theoretical thing, which is not really practically applicable as is. And Lyapunov developed, but this is just definition, okay? So Lyapunov developed theorems which are allowing us practically to test if something is actually Lyapunov stable or not Lyapunov stable. But try to understand, first of all, intuition, why that type of definition is important. Like, what does it mean to have that type of definition in physics, like physically? Can you describe the types of systems in physics which could be that type of systems? So the overall idea is that these are the systems where you do not have any additional energy introduced into the system. So starting with particular points, and yes, it can have some initial energy based on your initial position, initial x0, right? But you're not pumping additional energy into that system. So the energy could get only same or less. Okay, so you can preserve the energy, which means you're not moving, not doing anything. You can stay wherever you are, and then energy will not change at all. Or you can dissipate the energy, but you cannot introduce the energy into the system. This is what it means to be Lyapunov stable. You're not introducing any new energy into your system. The energy is the same or lower with time. This is what it means. And mathematically, that symbol, have you seen that symbol before? Which is norm. Technically, this is telling you distance of one vector from another vector, okay? And you can define norm in multiple different ways. In abstract way, norm is defined as some given function, okay? And this function should be 0 at 0 and positive for anything, for any other vector, which is not 0, okay? And you have also property of the triangle inequality, which means that the sum of two norms is always bigger or equal to the norm of the sum. Okay, this triangle inequality. So you have all kinds of properties for norms which are actually defining what norm is, and you can have multiple different norms. So you have, I believe, the following properties that, so if you have vector of 0, norm of 0 equals to 0, and this is the only vector which has that type of norm. So only 0 vector. This could be like 0, 0, 0, 0 vector, many zeros, as many as you want. So norm of the 0 is 0. Norm of any vector A is larger than 0 for A not equal to 0. Okay, for any other vector, it's positive. And then you have also additional properties that alpha times absolute value of alpha norm any vector like that is alpha A vector, then alpha is some given scalar, right? You have other property, which is A plus B, both vectors larger or equal, A plus B. So any function which is satisfying these things could be called norm. And you have multiple different norms. You have norm 2, norm 1, norm infinity, norm, all kinds of norms, okay? The most popular norm is Euclidean norm. And Euclidean norm between two vectors is just sum of the differences squared and square root of that, okay? It's same thing that you're doing distance in geometry, okay, between 2 points. So vector is practically a point in n-dimensional space. So finding distance between the points and Euclidean distance would be something like that. Would be like A1 minus B1 squared plus AN minus BN squared. This is Euclidean norm or norm 2, okay, for the square. Okay, so this is norm between vector A and vector B. Okay, taking elements, element by element differences squared, summing them all up, finding square root of z. This is distance between 2 points in n-dimensional space. And this is z norm, okay? But this could be any other norm, which means you have multiple definitions here in one definition. Depends on the norms that you choose. You can define that a little bit differently. All of the norms will have these properties. So this means that if you pick in radius larger than 0, there exists, which means you can pick another radius, also positive radius, okay, typically smaller, but this would be a function of r, such that if the distance of equilibrium point from your x0, and this is your equilibrium point here, doesn't have to be 0, actually, it could be, doesn't have to be origin, it could be any equilibrium point. So this distance from equilibrium point is less than that r, which means it's inside of that hypersphere, okay, around your equilibrium point in n dimensions. Then the distance from xt to x equilibrium point will be less than your radius, less or equal to your radius that you have picked originally. In general, I'm kind of repeating myself 100 times in a different ways. This is, you can write it mathematically, you can think about that intuitively, but this is the meaning of the theorem. Now, what happens with asymptotic stability now? Can you define the same way asymptotic stability for nonlinear systems? And if you remember, we dealt only with origin as equilibrium point for linear systems. We dealt with convergence to 0, so limit of the x's needed to converge to 0, because this is sum of exponents, so it must be converging to 0, right? But for nonlinear systems, this is not the case. So how would we define asymptotic stability for nonlinear systems where equilibrium point is somewhere, okay, and system is nonlinear? So here's the definition, very simple compared to the previous one. After you've seen the previous one, same thing, it should be Lyapunov stable, but the limit of the difference should go to 0. So it should converge to equilibrium point eventually, okay? But both need to be true, which means just convergence to 0 is asymptotically stable for linear systems, but not for any other systems. System might still be unstable and converging to 0 or whatever equilibrium point. We will talk a little bit about that type of systems, just to see that systems like that could exist at least. And here is a direct Lyapunov method, which is a little bit more practical for finding Lyapunov or asymptotic stability for nonlinear systems as they are, all right, without doing linearization and all of the other processes. And this is, I believe, called second method, based on how it was organized in his original book and thesis on the stability theorems. So this was his second method, which is called direct Lyapunov method. And we will assume for simplicity here that equilibrium point is 0, and we will handle all of the non-zero equilibrium points a little bit later, okay? So let's assume x equilibrium equals to 0, right? And deal with other equilibrium points later. We will define Lyapunov energy function. And just to remind you, this terminology of energy has nothing to do with physical energy. It's just mathematical energy, because the analogy is coming from physics. This is why it's called energy. And this function will be defined as follows. Very abstract definition. Function v, this is Lyapunov function. It will be scalar function of state x, which means you have multiple x1, x2, x3, x4, but the v function will be scalar function of it. What does it mean to have scalar function? It's one-dimensional, which means it could be like x1 squared plus x2 squared, for example. The single value function for a given vector x. So you substitute values of x1, x2, x3, x4, you get a number, not a vector. okay? So we will call that function Lyapunov function if it satisfies these four conditions. Again, very similar to all of that mathematical stuff where you're not saying what that function is, but you are defining properties of that function. And these properties will limit your class of functions that you really can use for it, okay? And sometimes it will limit to such an extent that you cannot find any. And this is where difficulty is, and this is why I mentioned previous times that sometimes you need actually to develop entire PhD to find that function for a particular system. To have some systems that you need to design the Lyapunov function for, it's like PhD work, a lot of work to figure out what that function is, to find such a function that does all of that for your particular system. And this is where it becomes very complicated. Okay, so v of x should be continuous function with continuous partial derivatives, which means all of the derivatives with respect to all of the x's are available. It's differentiable function and partially differentiable function. So you can find derivatives to dx1, to dx2, to dx3, and so on. All of them exist for that particular function. And you need to define that function. Okay, this is designer's choice, how you define that function. And typically you have multiple different possible functions which would work for proving or disproving your stability of your system. Okay. All right, so what we know is that all of these derivatives also continuous, which means this is a smooth function. You have continuous derivatives and all of them are continuous. Remember what continuous means in calculus? No disconnects in the function. Okay, it's all connected without jumps, without step responses anywhere. Okay, that kind of function. And a few more properties. So first of all, for all x's not equal to 0, attention to that thing, this function is positive as a function of x. Okay, v of 0 equals to 0, similar to norm. Okay, but here you have additional property, which is not property of norm. The derivative, and pay attention to this, is a scalar function, right? Derivative with respect to time, this is dot of v, should be not positive, 0 or negative. This is how you need to choose your function. Okay. So for all x in the neighborhood of the origin, which is that point. So around your equilibrium point, your function should have negative derivative. What does it mean, negative derivative? So positive derivative is positive slope, negative derivative is negative slope, right? Yeah. But it is 0 at that point, positive everywhere else, but the derivative is negative. It looks like a ball type of thing, right? But in an n-dimensional space. So this will be one-dimensional function, right? So this is interesting, that if you think about the function as energy, which is introduced to the system, or system has a particular point, that property practically means that you are not introducing new energy. You can keep the energy where the derivative will be 0, so v is not changing, practically speaking, or v will grow down, will not grow, it will decay down, how you say that. It will be dissipated. The energy will be dissipated, it will disappear practically with time, okay? Because this derivative is with respect to time. So v will get smaller with time if the derivative is negative, right? So if it is all the time kind of going down, 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 this is negative slope, right? Going down. V will get smaller, that's what it says, with time. So we want such a function which looks like that, right? Think about parabola there, looking up, okay? It's everywhere positive except that 0 point where it is exactly 0, right? So it starts with 0 point and then somehow going up like a bubble, okay? but it becomes like emptier and emptier with time. That type of function. So energy is going down this time. Now, if you want to compute derivative, which is v dot, supposed to be dot here, here's how you compute that. This is a way to compute derivative of that type of function, because this function of x1, x2, x3, so you have multiple partial derivatives. So you need to do derivative within derivative, right? Because x, each of the x's is a function of t, but v is a function of x. So you have that complex derivative rule where you need to multiply by inner derivative, right? So you're making derivative with respect to x, so it's d to dx and dx to dt multiplication. Remember that rule, chain rule? So you're using the chain rule of derivatives to compute that thing. And this is exactly the chain rules that you have here. So you're just multiplying dv to dx1 times f1 plus dv to dxn to the fn, and pay attention that f1 is x1 dot and fn is xn dot, right? So this is exactly the chain rules that you want, okay? Any questions so far? So this is just way to compute that a little bit easier than kind of opening all the things. You can compute it that way. All right, so we need to find that kind of function, and as I said, this is a very difficult task. But assuming that you found that kind of function, okay, we will see if you can. Sometimes you can, sometimes you can't. Here are the stability theorems from Lyapunov, okay, how you now can find stability, asymptotic stability and Lyapunov stability of the functions, given that function. So the equilibrium point, x equilibrium equals to 0, as we assumed before, is Lyapunov stable in the neighborhood, some hyperbole epsilon. Again, mathematicians like that type of symbolics. Again, think about that as a circle in state space, or it will be hypersphere in higher dimensional space, okay? So it will be stable in some particular neighborhood if there exists Lyapunov function v. That's it, as simple as that. So if you manage to find that function, if this exists, then it's Lyapunov stable. That's it. All right, so that's why this function is so important. Now, for asymptotic stability, it needs to be Lyapunov stable, which this function needs to exist. And this is the only difference here. That the derivative, this is supposed to be dot here. So the derivative needs to be always negative. And the difference from that thing is we remove that thing here. It cannot be equal 0. It always will be monotonically decreasing in time, right? This is the only difference. And this is reasonable. Why? Because if you're thinking about asymptotically stable systems, we define them as systems which are converging to equilibrium point. But if your energy in the system is not decreasing, which means you always have the same energy, so it can oscillate, it can do all kinds of other things, right? It will not converge to your origin point. It will still have that energy going on all the time. You want the energy to decay eventually to 0. And the only way that energy will decrease to 0 is that it will always kind of decrease. So this is a property. So you need to require v dot less than 0. Any questions on that theorem? I don't think that this is much easier than before, right? It's like you still need to find the function v, but at least you have some way to test. And this is a little bit easier than this definition. Because here you have infinite number of possible radiuses, infinite number of possible states, and how you even deal with that. So the proof of that theorem is based on the definition. And I'm not even showing that proof, okay? All these 50 pages of proof. But you can show that if function like that exists, then the system is Lyapunov stable. If this function exists, or asymptotically stable, if this function also satisfies that condition. All right? So a few notes. If you cannot find that type of function v, practically speaking, it means nothing. You don't know if the system is stable, unstable, you just cannot find it. So it's not useful. And this is again why people spend years to find that type of functions as their PhD. At least maybe like 20 years ago, people were doing PhD on that kind of stuff. Just find Lyapunov function for a particular plant. This was like years of work to figure out what that thing is. Sometimes it's very difficult for particular plants. Sometimes it's very easy, and you have nice library of functions which work for many different plants. So you can try all of them and see if any of them work. And if you find one, you actually prove that the system is stable around that equilibrium point in some neighborhood. Okay, what happens if your equilibrium point is not in the origin? It's not at the origin, so what should you do? It's not a problem at all, because you can define different state, and we will call that state Z. You can pick any variable. Let's call it Z. And your Z will be X minus X equilibrium that you have, and you want to check stability of. So pay attention what happens to that particular system, okay? With your new Z state, different representation of the system. So by definition, Z dot will be function, previous function, nonlinear function of some kind of X, which is Z plus X equilibrium, right? So I'm just taking that X from that equation, so it will be Z plus X equilibrium, right? This is what X is, practically speaking. But this one, if you take in Z dot here, you get X dot minus X equilibrium dot. But X equilibrium dot is what? Zero, it's constant. I mean, derivative of constant is zero, right? So Z dot equals to X dot. And this is why I can write it here as Z dot, because it equals to X dot, right? And it is function of Z plus X equilibrium, which is just computing that X from that equation. And that's it. So the equilibrium point, if you substitute the Z equilibrium, which is Z dot equals to zero, by definition of equilibrium, right? What it will be? It will be always zero, by definition, right? Because this function will be zero, or this one equals minus this one, again, by definition. So that type of system, you can investigate stability of that kind of system, which is practically shifted by a constant vector. And if this equilibrium point is stable, then the original equilibrium point is stable. If it is unstable, then the original point is unstable. It's just shift of the entire system into a different point. This is what other equilibrium points mean in that sense, okay? So for dynamic system to have other point of equilibrium outside of origin, it's just shifting the entire system into that space. So if it was stable, it stays stable. That's it, all right? Any questions on that? And now we can derive stability for linear systems from nonlinear system criterion of Lyapunov and to see what happens then. And we get very interesting equations. And this equations is also Lyapunov theorem for linear systems and checking stability systems, stability of linear time invariant systems using matrices A. And this will be very equivalent to, obviously, eigenvalues of A to be in the left semiplane or within a unit circle for discrete time systems. So that matrix equation that I will show in a second is related to eigenvalues of matrix A. And why do we care to write all of these equations down, okay? It has more theoretical interest here, so it's more important for theory because all of the optimal control will be based on these equations. So this is why I'm showing these equations and showing that they are completely equivalent to just checking eigenvalues of matrix A in terms of stability, like asymptotic stability, stuff like that. All right? So here is the theorem. Linear time invariant system, which is just x dot equals to AX. And you know that you can check stability of that system just by making sure that eigenvalues of A have negative real value, all of them. Remember that? Okay, for continuous time systems at least. So first theorem is for continuous time systems. It is globally asymptotically stable, which means no matter where your initial conditions are, you can start it anywhere in space, in n-dimensional space. Your x0 can be anywhere. it will be asymptotically stable, which means eventually it will converge. It will be Lyapunov stable and eventually converge to 0 point, to origin, if all of the eigenvalues have negative part. So you know that already, right? We stated that theorem. But now I'm adding kind of that term, just to emphasize that these systems are globally asymptotically stable, which means if your eigenvalues of matrix A are stable, no matter where you start, it will always converge. You cannot find such initial conditions from which it will diverge suddenly if your system is stable. You can start at minus 1 million, whatever. It will still converge eventually. All right. But now we have additional two things actually. So LTI system x dot equals AX is globally asymptotically stable if for some positive definite symmetric matrix P, which is positive matrix, the matrix, that kind of matrix is symmetric and negative definite, which is, well, kind of tricky to interpret. So let's try to interpret it. Who knows what positive definite or positive or negative definite or semi-definite or anything in that domain is? Who have learned about positive definite matrices in linear algebra? Never heard of it? Or don't remember? Big difference. I've seen it somewhere. Positive definite, positive semi-definite, or negative definite. Yes, so this is connected to positive eigenvalues. So there are, practically speaking, 4 different types of matrices that we need to be aware of. Okay, one type, which is the most important for us, is positive definite matrices. And positive definite matrices are defined in very particular way, which we will not really use, but I can write the actual definition, which maybe not that interesting, but theoretically very important. All right, to write it, let's see if you remember or know or heard about quadratic forms. About quadratic forms. Have you heard about quadratic forms or matrices? Who have seen quadratic forms anywhere? Okay, not many students seen quadratic forms. Quadratic form is relatively simple thing. Okay, it's defined by some vector T transpose times some matrix P times X. Okay, this is quadratic form. It's like px squared in a way, like quadratic term, but in vectors. So in vectors, you cannot do square because there is no meaning. Both of them are vectors like that. So you need to transform a vector like that, and then you have another vector like that. This will be quadratic form of that matrix P in the middle, right? So for that quadratic form, if this, and pay attention to the dimensions, okay? So this will be 1 by n, this will be n by n, and this will be n by 1. So what is the dimensions of that quadratic form? 1 by 1, which is scalar, practically it's a number. So for that form, you can say if it is positive or negative, because it's number, right? So if for all x's, this thing is larger than 0, then the matrix P is positive definite. This is how it is defined. If quadratic form of matrix P is positive in numbers, this number, for any x that you choose, so like pick any x, any vector x with any values, positive, negative, you pick any values you want. If for all x's, or any x's, this one is positive, then P is positive definite. If this is like that, larger or equal to 0, So for some x's is positive, for most x's probably it's positive, but for some x's it's exactly 0, right? And this is x not equal to 0, of course. Because for x equals to 0, no matter what p is, it's always 0, right? For vector zeros. So for any x not equal to 0, this should be positive for positive definite matrix. It could be larger or equal to 0 for positive semi-definite matrix. It could be less than 0 for negative definite. And it could be less or equal to 0 negative semi-definite. Okay, this is what it means. Now, obviously, it's difficult to check that condition for any x. You have infinite number of possibilities here, and typically you'll have, for that type of matrices, you will have expression which would be some constant from p multiplied by x1 squared plus some other constant times x2 squared, that kind of thing, and then you know that it is positive for any x's which are not 0, right? This is how you you need to combine all these terms in such a way that you'll have multiple squares multiplied by numbers. And then if it is sum of squares, then you know that this is positive always for anything which is not 0. So this is how you do that, theoretically. But practically, there is much better and easier way to identify if this matrix is positive definite. For all positive definite matrices, all of the eigenvalues are positive. Okay, this is how you know. You just check eigenvalues of the matrix. If all of them are positive, the matrix is positive definite. If all of them are negative, it's negative definite. If all of them are positive except few which are 0, then this is that thing, which is positive semi-definite. If you have all of them negative, but some 0, almost all negative, but some 0, then it's negative semi-definite. Right, so based on the eigenvalues, you know if it is positive or negative, semi-definite or definite. Any questions on that? And I'm clearly running here very fast on the linear algebra part because it's not really part of the course, but you really need to understand what that is. Okay. All right. So let's read it again. So this system is globally asymptotically stable for some positive definite symmetric. And symmetric, remember what symmetric means. So the matrix equals to transpose of itself. Practically speaking, the upper triangle is a reflection of the lower triangle of the matrix. This is symmetrical matrix. Okay, so you have such positive definite matrix P. Okay, and typically you would write that, and I'm using regular large sign, but in literature you'll find that type of sign. This is positive definite. Because we are talking about matrix, you cannot say P larger than 0. P is a matrix, you cannot compare it to 0, right? Something else. Okay, and sometimes you even have that kind of thing. What do you think this means? So this matrix is kind of larger than this matrix. What that could mean? Like obviously you cannot compare, like you have a bunch of numbers here and a bunch of numbers here. And you're saying P is larger than Q. You're comparing two matrices somehow. What does it mean?
That Q is Q value is under 0 actually. Q value is negative.
Q values are not 0.
If P is greater than 0.
P is positive. You're saying if P is positive definite, yes.
Yes, but Q could be negative.
Q could be negative, yes. But it doesn't have to. So this is just notation for that thing. The difference between the matrices is positive definite. Okay, this is just notation for that. And you see a lot of that kind of stuff in mathematical books and controls books. People are using that notation a lot, but they mean that. Actually, you cannot really compare matrices. You can just say if some matrix is positive definite or not. So this just says that P minus Q is positive definite. And they obviously should have the same dimensions, that you'll be able to subtract them, right? But this is side note. Okay, so the claim is that this matrix, which is A transpose, and A is coming from your system, obviously, times that positive definite matrix P plus PA is symmetrical and negative definite. This is the claim. And then it's asymptotically stable. Typically, we are picking particular matrix here. So we can pick any negative definite matrix here. So this would work for any negative definite matrix here. And I call it Q. But unless otherwise stated, I will always pick that as I. So Q will be equal to I. This is the easiest choice that you can pick here. So you can always think about that symmetrical negative definite matrix as minus I. All right? So you can read it in a simpler way. So this system is asymptotically stable if this matrix is positive definite when it is solution of that equation when Q equals to I. Right? So if you solve that equation, and this is a system of linear equations, practically speaking, so you'll have P matrix is symmetrical, so you'll be able always to write that as parameter like P11, P12, so you'll have numbers, right? All these parameters. And this linear multiplications, these are linear combinations of these values, right? So if you have linear combination of these values, this is a system of linear equations, and it equals to some constants, which is like minus ones on the main diagonal, and everything else is zero. You solve that system of equations, you find matrix P after you solve that system of equations. If this P is positive definite, then your system is asymptotically stable. And yes, I understand that this is much more complex way to prove asymptotic stability instead of just going and finding eigenvalues of matrix A, right? And checking if all of them are negative. That would be much easier for us. But this equation has a lot of power when we get to LQR, which is linear quadratic regulator, and other optimal control, and including the Kalman filter. All of them are using this equation to develop theory of optimal controls. Okay, and this is why you need to remember this is equivalent. And this was actually the original theorem that if you solve that equation, find the matrix P. If it is positive definite, then the system is asymptotically stable and goes both directions, is if and only if. All right? Questions on that part? We will solve some problems to see how it works later, but this is theoretical part first. Okay, so what happens with discrete time systems where all the eigenvalues need to be in the unit circle, right? So this is a statement of Lyapunov theorems for that case, where you have system which is xk plus 1 equals ax of k, all right? This is discrete time, linear time invariant system. Again, you know that you can just check eigenvalues and see if they're inside the unit circle, if the absolute value of all the eigenvalues is less than 1, practically speaking. And this is what that first thing is saying. So to make it globally asymptotically stable, all of the eigenvalues need to be less than 1, right? So absolute value is just distance from the origin to that point. Now, you have very similar theorem using just different matrix equation now. So discrete LTI system, discrete time LTI system is globally asymptotically stable if for some positive definite symmetrical matrix P, the matrix like that is symmetric and negative definite. All right, same theorem, just different matrix here. So if this one equals to minus I and gives you practically positive definite solution, then your system is asymptotically stable. And this is equivalent to that thing. Again, if and only if, in both directions. All right. A little bit tricky, but doable, I think. And we have a few comments on that. Any questions so far? So a few more things. This is the last part of the theory. All right. So, as I mentioned, you can choose any negative definite matrix on the right side of that equation, which I call minus Q. So Q might be any positive definite matrix, practically speaking. And that's, I mean, you can choose Q equals to I, or you can choose Q equals to whatever. That's fine. It could be diagonal, not diagonal. It doesn't matter that much. You just need to have something negative with negative eigenvalues on the right. All of them needs to be negative. And why is this one is negative? Like minus I is negative. Negative definite. Why is that? So I is definitely positive definite. What are the eigenvalues of matrix I? You don't need to calculate that. They're sitting on main diagonal. This is diagonal matrix. Eigenvalues of diagonal matrices, triangular matrices sit on the main diagonal. So what are the values? All of them 1. So all of them are positive. 1 is larger than 0. So all of them are positive. So I is positive definite matrix, right? So what is minus I? It's like minus 1, minus 1, minus 1, minus 1 on the main diagonal. So it's negative definite matrix because all the eigenvalues are minus 1 in that matrix. But you can pick any other values like minus 5, minus 7, minus 27, whatever, right? Whatever you like. All of them will work. More than that, it will work in both directions. So if it works for one matrix, it will work for any of them. All right, you don't need to check all of them. You need to check one. If it works for one, it will work for all of them. This is the theorem. That's why you have 2 parts to the theorem. Just saying like, yeah, you can pick one, and if it works, then it's asymptotically stable. If it is asymptotically stable, then it will work for all of them. This is like if and only if direction. So it's enough to check one if you want to check stability. And you can pick Q equals to I because this is simple and you have a lot of zeros, right? We love a lot of zeros in our equations. And now I think the most important part of that to remember is that second node. And second node says that for linear systems, we actually always can find Lyapunov function. And this Lyapunov function is the quadratic form of the matrix P. So you can solve that system of equations to find that P here or there, okay? This will be positive definite matrix. And obviously this will satisfy all of the conditions because for x equals to 0, V will be equal to 0, right? Obviously, because 0 times whatever is 0. Now, second thing that we know about V, right, also will work. Because what we are saying, like, remember what we said about V? So it should be always positive. But this is by definition of quadratic form. This is what positive means, right? This thing. This is how we defined positive definite matrices P. And if P positive definite, then clearly V will be larger than 0 for any x which is not 0, right? So the only thing that you need to prove is that V dot is negative of that function. And you can prove it. I will not. But if you're interested, we can actually do that. It's not too difficult. It's just derivative of that term. And you will show that you get some negative number here. It's always less than 0, right? So this function works. So we found explicit function for linear systems, which is a Lyapunov function and satisfies all of the conditions, which means satisfies all the Lyapunov theorems. And you can use that as example for Lyapunov functions. Okay, but typical Lyapunov functions look something like, I don't know, something like that. Or maybe some combinations of x's squared. Okay, this is typical function. If this doesn't work, and you cannot find coefficients alpha and beta, which would satisfy all of your Lyapunov conditions, Lyapunov function conditions, then you're in trouble going to PhD on that. Okay, I mean, if this doesn't work, and you have a few more kind of classical Lyapunov functions which are working for many different systems, nonlinear systems, right? Then it is difficult to find. Any questions? All right, let's talk a little bit about physics. Questions. Can you think about system which is Lyapunov stable, but not asymptotically stable? Physical system. And again, the difference is that in one system you always have dissipation of energy, and another you don't have to. And pay attention that systems which are asymptotically stable are always Lyapunov stable, which means you do not have systems which are asymptotically stable but not Lyapunov stable. So Lyapunov stability is kind of weaker type of stability. System can be Lyapunov stable but not asymptotically stable, but not the other way around. If you remember, same kind of thing happened to Bibo stability, right? So Bibo stability is kind of weaker stability in a sense than asymptotic stability, which is stronger stability, because you cannot have Bibo unstable system and asymptotically stable system. This cannot exist. But what I'm asking now can exist. You can have Lyapunov stable, asymptotically unstable. What kind of system is that? I showed you that system before, that type of system. And you haven't seen that many systems, so you can just take one class back.
The pendulum?
Almost close, yes. Not the pendulum one, because the pendulum one is obviously not stable, because if you try to put it like that, it will fall, right? But part of the system, yes. How about the card itself on flat surface? So what happens is, let's say you move that card to a particular initial condition. Will it return to the origin? Of course not. But will it move further or run away somehow? Also not. It will stay wherever you leave it, right? So this is a asymptotically not stable system. It will not return to the origin. This card is a very simple system. It's like you put in that card, you move in it, it stays wherever it is. Or any other object, it doesn't have to be card even. It's like any object on flat surface. So this is Lyapunov stable, which means you're not introducing any additional energy after you left it there. Okay, no new energy is coming to that to make it move somewhere. Okay, but it also will not return back. All right, so this is one of the examples of Lyapunov stable system, but asymptotically unstable system. It's not returning to the origin. Okay, so another question. Can you think about systems? This is a tricky question, much more difficult question actually. Can you think about system which is Lyapunov unstable, but always returning to the origin? And clearly this is not asymptotically stable, but still returning to the origin no matter what. And it's unstable system in any sense, but returns to the origin, like converging all the time, eventually. You have many different systems of that kind, which is even weird to think about, that that kind of thing may exist, that something is converging but not stable. At least it is defined as unstable in the sense, all of the senses that we learned so far. Okay, so in this sense, the systems are unstable, not asymptotically stable, not Lyapunov stable, not Bibo stable, not stable, period. Okay. So take a few minutes to think about, like, can you imagine the physical mechanism of some kind which would practically what you need to make it Lyapunov unstable? Think about the definition, right? No matter where you start initially, it will run away far first and then will return back to the origin somehow. Okay, so no matter from where you start, how close to the origin you will start, no matter how close to the origin you will start, it will always run above that big radius. Okay, so it will escape that radius and then it will return back. So no matter what radius you choose for me, I will not be able to choose like smaller radius from which it cannot escape from the bigger radius. But you always will try to escape. Maybe to a constant distance, or I don't know. So this is a little bit more difficult to find that kind of system. Yes. Doesn't have to be anything specific. Just think about the mechanism itself. Like what, let's say you need to invent that mechanism now that would do that specifically for the purpose of that question. Can you think about some mechanism which could do that? Hmm? Yeah. Yeah. This is, but you need additional energy. So kind of kicking it out. So your mechanism is like pumping something out and then it retracts back to the origin. And no matter from which place you retract it, it's like, I don't know, children's gun, you know, with the rubber band, okay, which attracts the bullet back to the gun, right? But you can start from any point to trigger it, okay? So you can throw it from anywhere on that inside the gun, okay? So you throw it out to a particular distance, okay? And then it retracted back to the origin always. So you have many different systems of that kind where you have to leave particular radius and then it comes back. So it retracts back, but before it comes back, it needs to go far. Okay, this is the idea of Lyapunov unstable and asymptotically unstable, but converging. Okay, it's called unstable. All right, another question. Can you think about linear systems which have equilibrium point not at origin? So X equilibrium is not zero. Can you think about linear systems like that? LTI systems. What is the solution of any LTI system? Linear system. Okay. Simpler question. How can you write solution of linear differential equation in general? Homogeneous linear differential equation. So this is what the system is. Sum of exponents. That's what we have. These eigenvalues in the powers of the exponents. So could sum of exponents converge to something which is not zero? What could that be? We have exponents, many exponents. Multiplied by some constants. sum of as many as you want. Could that converge to anything but zero? It can't. The only possible equilibrium point for linear systems is always origin, always zero. You cannot converge to anything else. Sum of zeros always will be zero. No matter how many zeros you add, still you'll get zero. So all of them converge into zero, because when t goes to infinity and this is negative, it's exponent of something negative t, eventually it will converge to zero. If you adding and multiplying that by constant will not change that fact, because constant times zero is still zero. And adding multiple zeros still converging to zero. So no matter what you do, it still converges to zero. All right? So it can diverge, go like that exponent, and that will be unstable, but then it will not converge. Right? This is not converging system, it's not stable. But if it is stable, it always converging to zero. All right? Any questions? Yes.
We have Lyapunov Stability for the continuous time systems, right? So do we have any for discrete time systems too?
So use Z transforms, yes. So it goes in parallel to Laplace transform for discrete time systems, yes. They have very similar properties of derivatives and other things like that. So instead of derivatives, you have delays. And Z transform of delay is same like Laplace transform of derivative. So they go in parallel. Okay, great question. Any other questions? All right, thank you.